Good day everyone. For this experiment, our title is Determination of Sodium and Potassium in Used Cooking Oil using a flame photometer. Used cooking oil is widely produced from both domestic and industrial cooking activities. When cooking oil is repeatedly heated and reused, it undergoes physical and chemical changes. During this process, inorganic contaminants such as sodium and potassium can accumulate in the oil. These alkali metals mainly come from salt added during cooking, food ingredients, cooking additive, and degradation products formed during frying. Over time, their concentration in the oil may increase.
The presence of excessive sodium and potassium in used cooking oil is a concern, especially when the oil is intended for reuse, recycling, or conversion into value-added products such as biodiesel. High levels of these metals can interfere with downstream processing, cause equipment fouling, and lead to catalyst deactivation. Therefore, determining the concentration of sodium and potassium is important for equal quality control, environmental assessment, and proper reuse or disposal of used cooking oil. To analyze these metals, flame photometry is used. Flame photometry is a simple and rapid analytical technique based on emission spectroscopy, where metal ions emit light at specific wavelength and when introduced into a flame.
In flame photometry, sodium emits a strong yellow light at a wavelength of 589 nanometers, while potassium emits light at 766 nanometers. The intensity of the emitted light is directly proportional to the concentrations of the metal ions present in the sample. However, since cooking oil is an organic matrix and cannot be directly introduced into the flame photometer, the sample must first undergo acid digestion. This process breaks down the oil and converts it into an aqueous solution containing dissolved sodium and potassium ions. The objectives of these experiments are to determine the concentration of sodium and potassium in used cooking oil samples using a flame photometer and to understand the principle of emission spectroscopy.
Next, I will explain the chemical reagents and apparatus used in this experiment. The chemicals and reagents used include used cooking oil, concentrated nitric acid, deionized water, sodium standard solution, and potassium standard solution. Nitric acid is used for the digestion process, while the standard solutions are used to prepare calibration curves. The apparatus and instruments used include an analytical balance, a hot plate, 100 ml volumetric flask, 100 and 250 ml beakers, pipettes or micropipettes, Wattman number 1 filter paper, a funnel, and a 100 ml conical flask. These apparatus are used for sample preparation, digestion, filtration, and dilution before analysis.
Assalamualaikum and good morning to Doctor. So today I will explain about procedure. So to determine sodium and potassium in use for cooking oil, first we need to filter the oil to remove any food particle, and then we need to wet 2 grams of the filter oil into 250 ml beaker. Add 10 ml of concentrate nitric acid and heat gently until the solution becomes clear. Allow the solution to cool, then add approximately 10 ml of deionized water, and then stir, filter, and dilute to 100 ml in volumetric flask. Prepare standard solution by diluting sodium and potassium stock solution to concentration of 0, 2, 4, 6, 8, and 10 mg per liter by mixing thoroughly and labeling each bottle. Warm up the flame photometer for about 50 minutes and set the wavelength to 589 nm for sodium and 766 nm for potassium. Zero the instrument with deionized water and adjust with the highest concentration standard and measure all standard to plot calibration curve. Finally, aspirate the digest oil sample and record the emission intensities for sodium and potassium, repeating each measurement at least 3 times for accuracy. Thank you.
Hi everyone. Now I will explain the results that obtained from this experiment. We have prepared series of sodium and potassium standards with concentrations which are 2, 4, 6, 8 and 10 mg per liter and measured their emission intensity using flame photometer. Starting with sodium, we observed that sodium produced higher emission intensity compared to potassium. This is expected because sodium emits very strongly at 589 nanometer, which makes it highly sensitive in flame photometer. As you can see in this calibration curve, the emission intensity decreased as the concentration increased. Moving on to potassium, the emission intensity recorded were much lower than sodium. The intensity showed a slight increase between 2 and 6 mgl per liter.
So now I'll be presenting the discussion part for the question 1, calculation of the Na and also the K concentration in used cooking oil. So the final volume of digested solution is V equals to 0.1 liter, and then the mass of oil sample is 0.002 kg. So the formula is provided in the manual. So by using a calculation of the concentration in the oil, that is mg over kg. So for the Na, after calculation, the result is 1.5 mg per kg, and for the K is 6.5 mg per kg. So the question 2, tabulation of findings. So the parameter for the sodium and potassium, for the sodium, the concentration from calibration is 0.03, for the potassium is 0.13. So for the final volume of digest, both are same, that is 0.1 liter. The mass of oil sample, both are same, that is 0.02 kg. So the final concentrations for the sodium is 1.5 mg over kg. So for the potassium is 6.5 mg over kg. So for question 3, comparison with literature or regulatory limits. So the concentration of sodium and potassium obtained are relatively low, with the typical range report for used cooking oil. So the potassium concentration is consistently higher than the sodium, which agree with the literature finding where the potassium originated from the food ingredients such as the vegetables and the seasoning salts, while sodium content may decrease during the repeating, frying and also the oil degradation.
I will proceed to question 4. So for the question, why is acid digestion necessary before flame photometric analysis? So basically, acid digestion is required because oil is an organic matrix and cannot be directly aspirated into the flame photometer. So the digestion process uses concentrated nitric acid and heat to decompose the organic matter, converting the oil into an aqueous solution containing dissolved sodium and potassium ions that the instruments can analyze. For question 5, explain the principle of flame emission. So flame photometry is an analytical technique based on the emission of characteristic wavelength of light when metals ions are introduced into the flame. So during excitation, the thermal energy of the flame excites the electrons of the metal ion to higher energy levels. And as the electrons return to their ground state, they emit light at specific wavelength. So the intensity of the emitted light is directly proportional to the concentration of metal ion present in the sample. So for the two possible sources of error in our experiment, the first one might be incomplete digestion. So if the oil is not fully digested, become clear or pale yellow, the organic particles may remain, which can clog the aspirator or interfere with the flame stability. Another error might be contamination. So the sodium is highly prevalent in the environment, including the skin or sweat. So handling glassware without gloves or using glassware that was not truly rinsed with distilled deionized water can introduce external sodium, causing a falsely high reading. So for the question 7, suggest an alternative analytical technique. So we can use atomic absorption spectroscopy AAS or inductively coupled plasma optical emission spectrometry, which is ICP-OES. These methods are often more sensitive and can handle a wider range of elements compared to a simple flame photometer.
In conclusion, this experiment was conducted to determine the concentration of sodium and potassium in used cooking oil using flame photometry after acid digestion. This digestion process was important to break down the oil matrix and convert the metals into a measurable aqueous form. Based from the results obtained from the digested oil samples, the concentration of sodium was relatively low, ranging between 0.02 to 0.03 mg per liter. In contrast, potassium showed higher values, ranging from 0.13 to 0.15 mg per liter. This indicates that potassium is present in a higher amount compared to sodium in the used cooking oil. The higher potassium content may be due to contamination from food ingredients or salts used during the cooking process. Although the standard solutions for sodium and potassium were prepared, the emission intensity values did not show a clear increasing trend with concentration. This suggests that there may have been any experimental limitations, such as instrument instability, errors in standard preparation, or improper calibration. As a result, while the relative comparison between sodium and potassium can still be discussed, the absolute accuracy of the measured concentration may be affected. Overall, the experiment successfully demonstrated the application of flame photometry in analyzing alkali metals in complex samples such as cooking oil. For future improvement, better calibration procedures, repeated measurements, and proper instrument optimization are recommended to enhance the reliability and accuracy of the results. And that is all from our group. Thank you.